Have you ever wondered why a diamond is so hard, but a piece of glass can break so easily? Or why a metal spoon can conduct heat, but a wooden spoon cannot? The answers to these questions lie in the structure of solids. They are a state of matter in which the particles are held together tightly in a fixed position. This is why solids have a definite shape and volume. Solids can be made up of atoms, molecules, or ions. Imagine you're standing in a room full of people. Everyone is moving around randomly, bumping into each other. This is like what the particles in a gas are doing. Now imagine that you freeze everyone in place. This is like what happens when a gas cools down and becomes a solid. The particles are still there, but they're now held in a fixed position. What do you think would happen if you tried to walk through a room full of frozen people? It would be pretty difficult, right? The frozen people would block your path. This is why solids are generally hard. The particles are held together so tightly that it's difficult to move them around. Other properties of solids include definite shape and volume. They have a definite shape and volume because the particles are held in a fixed position. Incompressibility. Solids are difficult to compress because the particles are already packed tightly together. Brittleness. Some solids are brittle, meaning they can break easily if they are hit or dropped. This is because the particles in brittle solids are held together by weak forces. Can you think of any examples of brittle solids? Some examples include glass, ceramics, and ice. Let us dive a little deeper. Let's shrink to the level of atoms.
Imagine you're a tiny particle inside a solid. You're surrounded by other particles, all held together tightly in a fixed position. You can't move around very much, but you can still vibrate. What do you think would happen if you vibrated really hard? If you vibrate hard enough, you might be able to break free from the other particles and escape into the air. This is how solids evaporate. For example, when a piece of ice melts, the water molecules vibrate so hard that they break free from the ice and escape into the air as water vapor. The structure of a solid determines how the particles vibrate and how easily they can escape. This is why different solids have different properties. Crystalline solids. They have a regular and repeating arrangement of particles. This arrangement is called a crystal lattice. The crystal lattice determines the properties of the solid. For example, the strength and hardness of a solid are determined by the crystal lattice. Can you think of any examples of crystalline solids? Some examples of crystalline solids include metals, ceramics, and gemstones. These solids are used in a wide variety of applications because of their strength and durability. For example, metals are used to make cars, aeroplanes, and bridges. Ceramics are used to make tiles, dishes, and spark plugs. Amorphous solids. They do not have a regular and repeating arrangement of particles. Instead, the particles are arranged in a random manner. This random arrangement of particles gives amorphous solids different properties than crystalline solids. For example, amorphous solids are often more brittle than crystalline solids. Can you think of any examples of amorphous solids? Some examples of amorphous solids include glass and plastics. These solids are used in a wide variety of applications because of their versatility. For example, glass is used to make windows, bottles, and lenses. Plastics are used to make packaging, toys, and medical devices. The structure of solids is a fascinating topic, and scientists are still learning new things about it all the time. By understanding the structure of solids, we can develop new materials with new and improved properties. But solids do not remain solid if and when heated. Let's see how a typical solid responds to heating or thermal stress. When a solid is heated, the kinetic energy of its particles increases. This means that the particles move faster and collide with each other more frequently. As a result, the particles begin to break free from the crystal lattice and move around more freely. When enough particles have broken free from the crystal lattice, the solid will melt and become a liquid. The melting point of a solid is the temperature at which it melts. It depends on the strength of the forces of attraction between the particles. For example, solids with strong covalent bonds have high melting points, while solids with weak van der Waals forces have low melting points. Some examples of solids with different melting points are ice. It has a melting point of 0 degrees Celsius or 32 degrees Fahrenheit. This is because the hydrogen bonds between the water molecules are relatively weak. We are making a video on various types of bonds where hydrogen bonds are discussed at length. Iron. It has a melting point of 1538 degrees C or 2800 degrees F. This is because the metallic bonds between the iron atoms are very strong. Diamond. Strangely, it has a melting point of 3550 degrees C or 6442 degrees F. This is because the covalent bonds between the carbon atoms are the strongest bonds that exist in nature. The energy required to melt a solid is called the heat of fusion. The heat of fusion is the amount of energy that must be added to 1 mole of a solid to melt it at its melting point. The of a solid depends on the strength of the forces of attraction between the particles. The melting point of a solid can be affected by a number of factors, including pressure. Increasing the pressure on a solid will increase its melting point. This is because the pressure forces the particles closer together, making it more difficult for them to break free from the crystal lattice. Water is an anomaly. Impurities. It can lower the melting point of a solid. This is because the impurities disrupt the crystal lattice and make it easier for particles to break free. Surface area. Solids with a larger surface area will melt faster than solids with a smaller surface area. This is because the particles on the surface of a solid have fewer bonds to break than the particles in the interior of the solid. Enough of theory now, let us look into the application of solids in the real world. Solids are all around us. From the buildings we live in to the devices we use, solids are essential to our modern world. Imagine a world without solids. No cars, no aeroplanes, no houses, no computers. It would be a pretty inconvenient place to live. They are used in a wide variety of applications, including construction. Solids, such as concrete, steel, and wood, are used to build our homes, offices, and other structures. Electronics, silicon, copper, and gold are used to make the electronic devices we rely on every day. Medicine. Solids, such as titanium, ceramics, and biocompatible polymers, are used to make medical implants and devices. Transportation. Aluminium, steel, and carbon fiber are used to make cars, aeroplanes, and other vehicles. Can you think of any other examples of how solids are used in our everyday lives? Some other examples include packaging. Solids, such as paper, plastic, and glass, are used to package food and other products. Clothing. Solids, such as cotton, wool, and polyester, are used to make our clothes. Furniture. Wood, metal, and plastic are used to make our furniture. Solids are an essential part of our world, and they play a vital role in our economy and our quality of life. What do you think are some of the most important applications of solids? Some of the most important applications of solids include infrastructure. Solids are used to build our roads, bridges, and other infrastructure. Energy. Solids are used to generate and store energy. For example, solar cells are made of solids and batteries are filled with solids. Manufacturing. Solids are used to make the products we rely on every day, from our phones to our cars to our food. In the next episode, we will look into liquids in great detail. Make sure to like and subscribe to never miss an update.